I guess we're right on time, so we should get started. So remember, we were covering memory interference and quality of service, another fascinating area in computer architecture and computer systems in general. And we're going to continue that today. And this is what we did yesterday. We talked about shared versus private resources, memory interference, and the quality of service problem. And we did cover a lot of ideas, a lot of new ideas, different ideas in memory scheduling. Today, we're going to wrap that up, cover a few more ideas. This is not to mean that the ideas are done. I think this is actually a fascinating area. There's a lot more to be done. And this will become more important going into the future. Because if you look at any kind of system, memory controller is becoming a more central part. Here, for example, memory control is shared by everything, actually. All of the accelerators, all of the cores. Whatever is trying to access memory is going through the memory controller. And you have to have a scheduler and maybe other mechanisms in there to make it work, and to make it work well. Is this sound okay for everyone? Okay. Maybe one of my ears is closed. That doesn't help. Balance is good for everything. You cannot partition one of your ears and not hear from here. Okay, so we're going to wrap that up. And if you have any ideas on this one, I'd love to hear them. This is something that's really close to my heart, actually, because I've designed a lot of memory controllers so far, and I plan to design more, actually. But there's more to be done, for sure. And we'll talk about this after that, other approaches, not just memory scheduling itself, but what else can we do to mitigate the memory interference and control it. And then we will move to caches, because caches are another shared resource. And as I mentioned earlier, caches are closer to the processor. As a result, existing processors incorporate more of these techniques that provide quality of service in the caches, at least in the general purpose domain. So a lot of the memory schedulers that we're discussing in the heterogeneous domain, they actually have quality of service mechanisms. Maybe not exactly everything we've discussed, but they actually have quality of service mechanisms to ensure that accelerators are making progress. Like the dash memory scheduler that we talked about before we parted yesterday, that is actually a step beyond what's implemented in existing systems, maybe a little bit more complicated, maybe a little bit more comprehensive. But a lot of the ideas of tracking progress is already there in heterogeneous memory schedulers. Okay. I think you've seen this before. We'll see more. So this is where we left off. Predictable performance, strong memory service guarantees. The dash memory scheduler actually tried to do this a little bit, but not within a multi-core system. So it actually, if you know the performance requirements of an accelerator, and if the access patterns are predictable, you could satisfy those performance requirements with memory scheduling, assuming you can handle the interference that's coming from other resources. That's an easier problem, because you know exactly how many frames per second you need to satisfy, for example. But there's a harder problem, which is actually, what do you do with these guys over here, where you may not exactly know what the performance requirements are? You have these heterogeneous agents. Some of the performance requirements are very well known, and you can actually schedule. Based on that, you can predict the future a little bit. But there are also agents where the performance requirements are not perfectly well known, because you don't have, for example, a frame rate for a CPU application, but you may have a sense of, oh, I don't want to slow down this application by more than this much. Right? Then the question becomes, how do you allocate the resources to these heterogeneous agents to mitigate the interference and provide predictable performance? So we'll cover one approach, focusing on the CPU part. How do you estimate the slowdown of an application over here in the CPU more accurately? And let me give you the high-level approach. Basically, that's the goal is here. This is the grand goal. You want to satisfy the performance or service level agreement requirements in the presence of all of these shared resources. And memory and storage is a shared resource also. One approach to this is to develop techniques and models to estimate the performance loss of an application in the presence of resource sharing. Remember stall time fair memory scheduling that we discussed? It tried to do this, actually, but it didn't do a good job. I said that its accuracy was relatively low because it couldn't estimate the interference, the impact of interference that's caused by another request on this application's slowdown, and we will examine why. So if you can accurately estimate this performance loss, let's say perfectly estimate it, then you know exactly how much you're slowing down this application while you're running it together with other applications. And then you can design resource partitioning or prioritization mechanisms that can try to balance or that can try to satisfy a performance goal for all applications. If this application should not slow down by more than 2x, you try to satisfy that. If you cannot satisfy that, you punt and you say, I cannot satisfy it, so don't schedule these applications together on my multi-core system, right? You could actually have feedback loop to the system software or a data center scheduler, wherever you're trying to do this at. Of course, the goal is all the while providing high system performance, because if this is not a concern, this problem is really easy. You can over-provision your resources, waste a lot of money, cost, energy, and satisfy the performance guarantees. That's what's happening. That was what was happening for a long time, as we've discussed yesterday. Okay, so we're going to cover this work as an example work over here, because it has an insight that simplifies the problem. And maybe we'll cover this later after we talk about caches. But these are some predictable performance readings. We're going to look at this later on because it talks about source throttling, an alternative approach. This can also provide predictable performance, actually. But we're going to look at this one first, and then maybe this one later. Okay, let's jump into this one. So what's the problem again? We have an unpredictable slowdown in different applications. So if this application runs with this application, its slowdown is 2x. If it runs with this other application, its slowdown is 5x, because it depends on the characteristics of the application you're running with. And we don't want that. We want to have, if for example, for this 3D modeling application, our performance requirement is it shouldn't be slowed down by more than 2x compared to a reference system that we know it's slowed down on. This is not acceptable, clearly, right? Maybe we don't care about this other application as much when we're running it for throughput. Okay, so there's clearly a need for predictable performance, which we discussed when multiple applications share resources, especially if some applications require performance guarantees. And I'll give you a couple more examples. In mobile systems, for example, interactive applications run with non-interactive applications. I said this before. You need to guarantee performance for interactive applications, otherwise you'll have significant discomfort for the user. I don't think I would use this if I didn't have my requirements satisfied, and I become pretty annoyed, actually, when my requirements are not satisfied in this, right? I'm sure you do, too, and you should. And in server systems, different users' jobs are consolidated on the same server. You need to provide bounded slowdowns to critical jobs where you have service-level agreements. So the goal is to provide predictable performance in the presence of memory interference. So there are two things that we would like to do for this. First, estimate the slowdown as accurately as possible. And that's a hard problem in itself. Once you estimate it, use those estimates to control the slowdown. So let's look at how we estimate the slowdown first. So definition of the slowdown, you've seen this before, but this is really the performance alone divided by performance shared. Performance alone is the alone performance of an application on a reference system that you know of, perhaps. And performance shared is the shared performance of that application on the same system when it's running together with other applications. Ideally, this should be one, right? You should never slow down. But when you have resource sharing, it's very hard to satisfy that to be one. Okay, so there are a couple of key observations in this work that improve upon previous works. And the first observation is that if you have a memory-bound application, if your performance is mainly limited by memory, performance is correlated by the memory request service rate. This is actually true for non-memory-bound applications also, but it's easier to estimate for memory-bound applications. Basically, this is data from real systems. It's done with a synthetic application that hogs memory bandwidth. So you can control that synthetic application to hog a lot of memory bandwidth or no memory bandwidth. And you run it together with this application. This is a network simulator that I discussed very briefly yesterday from Spec 2006. And we look at the performance of this application, execution time, basically, of this application. Well, higher is better in this case, so it's really performance. It's the inverse of execution time of this application when it's given more memory bandwidth, when its request service rate increases. So if the interfering application is interfering a lot, the request service rate reduces. It becomes 0.35 over here. And if the interfering application interferes less, the request service rate of this application is the same as its alone request service rate. The takeaway over here is the normalized request service rate correlates very well with normalized performance. Basically, as your request service rate increases, you get higher performance. And it's linear, because this application is relatively memory bound. And this is a result in a real system. And you can actually make this, redo the study for different applications, and you get similar results. Make sense?
But maybe for some application, we might also get some kind of steep curve,
Yeah.
but it's not so much sensitive to the application.
That's right. So if the application is not memory bound, that's right. That's why I wanted to say this over here. This curve may not look exactly like this. When you're memory bound, that's what you get. And if you stop being memory bound at some point, maybe you taper off, right? Okay. So this means that you could actually rewrite this equation and estimate performance as request service rate. So slowdown is now request service rate alone divided by request service rate shared. So you don't need to directly estimate slowdowns anymore. You do need to directly estimate somehow the request service rate. And this is easy, as we know, because when you're running together with another application, you can simply count the requests that you are getting serviced per time, let's say. The harder part is this one. But it turns out we're going to look at some mechanisms that estimate this much more easily than slowdown. So the second key observation, and we will leverage the second key observation for that purpose. So if you want to estimate the request service rate of an application alone, while it's running together with other applications, you can do that by giving the application the highest priority in accessing memory. So remember, stall time for memory scheduling, we tried to estimate the slowdown by trying to account for the cycles where the application receives interference from another application. We're not going to do that anymore. What we're going to do is, if you want to estimate the request service rate of an application, we're going to give it high priority for a while, and we're going to observe what happens. So if you get high priority meaning you're the highest ranked application in the memory scheduler, that means that you're going to receive little interference. So it's going to look like you're running alone. It's not perfectly that way, of course, because there's other interference that was caused in the row buffer, ... and you cannot perfectly control it. But it's a little bit better. Basically, it's almost as if the application were run alone. So let's take a look at this. This is the requests that you have when this red application is running alone in the same system. And this is the service order, and this is the time unit. So it stalls for 2 time units. When it's run together with another application interferes with this application's requests. So this application slows down by 1 more time unit, as you can see. Now, if you give this application the highest priority for a period of time, what will happen is the service order will look like this when it's running together with the other application. So now you can see that, oh, I have 2 requests that are served within 2 time units, so my request service rate alone is 2 per 2 time units, right? So that's the idea, basically. Of course, this is not perfect. This is idealized, right? Because we're not. I'll actually make this picture less ideal later on. But that's the theory. Okay, so the model now is very simple. Memory interference-induced slowdown estimation, or MICE model for memory-bound applications, is basically this. Request service rate alone, as estimated by what I just discussed, and request service rate shared. And this is really easy to compute. So one question over here is, how often do you give highest priority to this application? Whenever you want to estimate the alone rate, request service rate of that application, you give it highest priority. Of course, you want to do this for the application that you really care about. So once in a while running applications together, you rank this application as the highest, and during that time, you observe the request service rate of that application and estimate that as the alone request service rate. So you do interfere with the memory scheduling to estimate the request service rate of this application a little bit. But again, that's better than the approach of descheduling the application and running this application alone for a while, right? Which is bad for throughput. Okay, the third key observation is for a memory-bound application, if you have no interference, well, let's take a look at how a memory-bound application actually behaves first. You have a compute phase, and then you have a memory phase. If you have interference, the memory phase lengthens. Because it's memory-bound, this compute phase almost doesn't matter, basically. Memory phase slowdown dominates the overall slowdown. Of course, this is, again, we're idealizing it, and all of this will lead to the error that we get in the model later on. But this makes life easier, basically. So the memory phase slowdown dominates overall slowdown, so you can actually estimate the overall slowdown as only the memory phase slowdown. But for a non-memory bound application, that's not the case. Basically, most of the time, this application spends in its compute phase, and the memory phase is little. And these are basically stored to memory. And if you get interference, this memory phase increases, so your performance loss increases. So we're going to designate this memory phase as a fraction of the execution time of this application as alpha. And this will be 1 minus alpha. So this application spends 1 minus alpha fraction of its execution time on the compute phase and alpha in the memory phase. The slowdown it experiences will basically scale only this part. This is actually true for non-memory bound applications also. So you could actually use the same model for both applications. But it turns out it's not very easy to estimate the overlap. But I'm not going to go into the detail. You can read the paper for that detail. But basically, we're really, because there is not much overlap in a compute-bound application between memory and computation, we really want to scale this memory phase, the fraction that, of time the application spends on the memory phase. Okay? That's the idea. So basically, this is the slowdown estimation model for non-memory bound applications. For memory bound applications, you don't need to do this because they're mostly memory bound. This is a good estimator of the overall performance. But for non-memory bound applications, there's a huge compute phase that is really not represented very well by this equation. As a result, we complicate the equation a little bit. We don't change the compute phase because of interference, but we do change the memory phase length. Does that make sense? Okay. There's still room for improvement in this model. So if you have interest in this, there's more to do. Okay, so how do you implement this? Again, with many other mechanisms, we have interval-based operation. In an interval, time interval, you measure the request service rate for an application, shared, and alpha also. You can measure alpha easily, right? At least while receiving interference. And you estimate the request service rate alone, in this case. And then you estimate the slowdown at the end. And in the next interval, you basically apply policies based on that slowdown. And then you measure the slowdown, estimate the slowdown for that interval during that interval. Basically, you do predictions based on the previous interval for the next interval, just like in other policies that we've seen. So this is prone to all of the issues that we discussed on interval-based mechanisms. If your interval is too long, you may not be able to adapt to the behavior of the quickly changing behavior of the applications, as you can see, right? If your interval is too short, your measurements may not be very accurate because you may not be able to observe the behavior of request service rate. That's a bit unfortunate. And it's always good to question these mechanisms all the time. This is easy to implement. That's why interval-based mechanisms make a lot of sense, actually. If you look at a lot of system mechanisms, they're interval-based, right? Operating system schedules applications based on intervals. It makes decisions based on intervals. Data center schedulers make decisions based on intervals. But maybe there's a better way of doing this. Maybe you actually invoke this when you've changed phases in the application. So if you, for example, know that the behavior of an application changes at some point in time, and if somebody conveys that to you, maybe the programmer, you invoke this estimation of the slowdown only at those boundaries. That's a possibility. And people have actually examined that. We're not going to talk about that as much, but they haven't examined it in this context of memory interference as much. Okay, so implementation, how do you measure RSR shared and alpha? Basically, this is easy, as I said, per core counter to track the number of requests serviced. And at the end of each interval, you basically divide that with the interval length. How many requests per second or per cycle? And memory phase fraction is also easy. You count the number of stall cycles at the core and compute the fraction of cycles stalled for memory for a non-memory bound application. Or a memory bound application also. Okay, this is the harder part. You want to estimate request service rate alone. And as I said, you would like to periodically give each application the highest priority in accessing memory. And how do we do that? We divide each interval into shorter epochs. That long interval gets divided into shorter epochs, similarly to what we've seen before with thread cluster memory scheduling. At the beginning of each epoch, the memory controller randomly picks an application as the highest priority application. And at the end of an interval, for each application, it estimates this, basically. Request service rate alone can now be expressed as number of requests during the high priority epochs, How many requests did this application get serviced while it was the highest priority application? While presumably it was not receiving interference from any other application. Divided by number of cycles during which that application was given the highest priority. So theoretically, this should give you the request service rate alone. Of course, it's sampling based, as you can see, right? You may not be able, it's prone to error because while you're sampling, meaning when you're giving highest priority to that application may not be doing behavior, having a behavior that's representative of its overall behavior, right? Just like with any other sampling technique, this is prone to error. And you can imagine in more intelligent mechanisms, maybe you give highest priority to this application when you think this application is actually accessing memory a lot, right? But we don't do that. Okay, so clearly there's inaccuracy. I've given you a bunch of inaccuracies, but there's one more inaccuracy in estimating this. When an application has highest priority, it still experiences some interference. We're not able to completely eliminate that interference, and this is difficult to do. Let me give you an example of this. So let's look at the request buffer state for this application for which we're going to give high priority. When it's run alone, this is what you see, right? And when the other application is run alone, this is not when it's run alone. This is when it's running together with another application. This is the first time step. You have this request serviced at the end of the first time step. And another request comes from another application. It starts getting serviced. But in the middle of the time, while it's getting serviced, another request from this application for which we gave high priority comes. You cannot deschedule this one and service this one. As a result, you have to wait. This has to wait for a while until it gets scheduled. So this still receives interference from this blue application, as you can see, right? Because of the arrival of, it so happened that this blue application, which has lower priority, its request arrived just a little bit before this red application's request. And while we're giving highest priority to this application, we cannot deschedule this request and reorder it. And as a result, this request needs to wait. I guess you could deschedule it, but then DRAM doesn't allow you to do that.
Downside may also cause starvation for the maybe compute bound application during this. Because if you are giving highest priority for this application, let's assume it's more memory bound, so it may cause starvation. So it may in turn, though you're estimating, but it may in turn the slowdown of these.
Yeah, that's right. So this is an intrusive technique. It basically, while you're estimating the slowdown, you're really intruding to the other applications. So you're really changing the behavior a little bit also. But while you're estimating the slowdown, even when you're estimating the slowdown, you may not be accurately estimating it. That's the point here. Okay, so this is one source of inaccuracy. You can imagine other sources of inaccuracy. For example, it's difficult to estimate in general the memory level parallelism of an application, because when you actually give highest priority to this application, you may not actually be having the same memory level parallelism as if you were running alone, right? Because you've changed the patterns completely. Interference actually changes the memory level parallelism patterns completely. And that's caused another error. And there are other errors that we're not going to talk about, like write, read, right? How does that change? We haven't talked about that as much, actually. We've talked about that in the past. If you remember, the memory scheduler changes between epochs of writes and reads. You cannot do reads and writes at the same time. You do writes for a while, and existing memory schedulers batch the writes. And if the writes are more than some threshold of the buffers, number of buffers, you go into the write mode. And then once the write mode ends, you go into the read mode. Now, because of interference, what might happen is you go into write mode much more often. One application may have a lot of writes. Another application may have a lot of reads. Now, you may be forced into going into write mode a lot. And this is a problem that's actually open that has not been taken into account in a lot of these mechanisms. Okay. So let me go back. I've derailed a little bit. But basically, there's this problem. So how do we actually try? This problem is actually pretty bad. That's why we want to fix it a little bit. So the solution for this is we still want to have interference in this estimation. We want to determine and remove those interference cycles from this RSR alone calculation. And the idea is this, basically. The equation is not as beautiful anymore. The equation needs to take into account this estimate of interference cycles. And what is that? Basically, a cycle is accounted for as an interference cycle if you have a request from the highest priority application that's waiting in the request buffer, but you're servicing another application's request in the memory scheduler. So this is a little bit like what we've discussed for stall time fair memory scheduling. And it's very hard to get away from this. And that hopefully shows you the difficulty of estimating interference. And if you don't do this, actually, your estimates of slowdown are not as good as if you do this. Okay. Okay, so let's put it all together. Basically, this is the model. As I said, this is interval-based. Well, I guess I've given you all the model. Putting it all together, I don't have the slides because I've used all the slides before. So let's evaluate this model. We've seen some of these previous works. Stall time fair memory scheduling was actually the first work that tried to estimate these slowdowns. But as I said, it didn't do a good job. It was not as accurate. We're going to talk about this. This is going to also estimate the slowdowns, but it basically builds upon stall time fair memory scheduling, and it does it uses it for a different purpose. So its accuracy is not as good either. And this is another work that tried to do cycle accounting in a different way. But basically, all of those works try to figure out for each cycle, am I receiving interference? If I'm receiving interference, I'm going to account for it, and I'm going to say that, subtract that from my shared execution time, right? Basically, this is the basic idea. You have stall time alone, stall time shared, and this is easy to estimate. This is hard to estimate. And all of these works basically count the number of cycles the application receives interference without giving it higher priority. So with mice, the first advantage is, well, the previous work estimates alone performance while an application is receiving interference. This is hard. When you're receiving interference, if you're not giving it higher priority, then there are so many effects that you cannot control for. So the key realization of mice is, if you give it high priority, you make the problem a little bit easier. It's not easy, but it's easier than this one. At least you eliminate some source of interference. That would be one of the reasons why this will be much more accurate. The second advantage is, basically, at least stall time fair memory scheduling doesn't take into account compute phase for non-memory bound applications, and mice accounts for the compute phase. As a result, it has much better accuracy. Actually, there's one more thing over here, if you think about it, that's not expressed in this slide, and that's the fact that these approaches, STFM and FST and per-thread cycle accounting that we will talk about, or we may not talk about, they all operate on a request granularity. They basically try to look at every single request and how much interference you get for every single request. That's a very fine granularity. Whereas if you look at mice, it's not looking at per request, except for the interference cycles that we've seen, that little fix that we tried to do. It's really looking at request service rate, which is really the aggregate behavior of many requests. And that actually improves the accuracy as well, because per request, you may make a lot of errors, and those errors compound. Whereas if you look at the overall request rate, you can estimate things better. So in a sense, I like describing these techniques as they're missing the forest for the trees, the per request techniques. They're very myopic. If you look at a bigger interval and the request rate, you're really looking at the forest of requests that in the end affect your performance in aggregate. Okay, any questions before we move to evaluation? Is this fun? Yeah. Okay, if this is fun, now you can imagine how much more fun it is to estimate the overall performance of an application when it's running in a data center. You need to take into account these effects plus many, many other effects. We're just looking at memory here. Okay, so let's look at the methodology. Well, you can read the paper for methodology, but this paper's methodology is quite good, actually, because it looks at a large number of multi-program workloads in simulation. So let's look at one application over here. This is Leslie 3D, what I showed earlier. It's a 3D modeling application. This is the actual slowdown it gets when it's run together with 3 other applications. It doesn't matter which other applications they are. This is the estimate with stall time fair memory scheduling. As you can see, it's not very good. It may be good for its purposes, but it's not good for predictable performance purposes. And this is the estimate you get with mice, which is not terrible. You don't perfectly track it, but you're really close. And these are different applications. I think the top ones are memory bound. So the memory bound applications, stall time fair memory scheduling does not too bad, but mice is still much better in keeping track of the actual slowdown. For non-memory bound applications, stall time for memory scheduling actually is not good. As you can see, it overestimates the slowdown because it doesn't take into account the compute phase. So maybe that's not a very fair comparison because it was not designed to take into account the compute phase of an application. That's fine, but it's still not good. So you really need to take into account the compute phase. Okay, so basically the average error across 300 workloads of mice is about 8%. So you can estimate the slowdown within 10% accuracy, whereas STFM is within 30%. So this is much better, actually. You can try to get something more interesting with predictable performance. So let's take a look at how you can use it. There are many, many potential applications. I'm going to give you one. I'm not going to talk about the second one. If you're interested, you can read the paper. But we'd like to provide soft slowdown guarantees. Why is it soft? Because you don't want to use this in your, again, anti-like braking system. Because you don't want your error to be 10%, or you don't want your error to be not bound, right? You really want worst-case estimation in that case. Or real performance isolation. Here, we can only do soft slowdown guarantees. We're going to violate the guarantees, as you will see, because we have estimation error. So the goal is to have, ensure QoS critical applications meet a prescribed slowdown bound. And this is actually very relevant in data center workloads or interactive workloads over here, where you can tolerate some error in the slowdowns, right? And of course, given this, we would like to maximize the system performance for other applications for efficiency reasons. And the basic idea is to allocate just enough bandwidth to the quality of service critical application that's not such that it meets its slowdowns, and assign the remaining bandwidth to the other applications. And this is memory bandwidth in this case. Okay, so basically, this is one mechanism. It may not be the perfect mechanism, but you can build many, many mechanisms on top of the slowdown estimation. You assign an initial bandwidth allocation to the quality of service critical application, and you estimate the slowdown of that application using this mice model. And every n intervals, if the slowdown is greater than some bound plus some error, you increase the bandwidth allocation. If the slowdown is less than the bound, then you decrease the bandwidth allocation. And that's the idea. This, one of the reasons why this may not be a great mechanism is it's interval-based again, right? What if the application behavior is not changing a lot? Then you don't need to really increase and decrease. You don't need to go into this mode where you don't have hysteresis, as we've discussed in the past, right? So you can actually improve upon this mechanism. But this is just an initial result that I'm going to show you. And if you don't meet the slowdown bound for n intervals, then you give up, basically. You notify the operating system so that saying, don't schedule this many jobs on this multi-core because I'm not able to satisfy the requirements. And maybe the data center scheduler, right? Data center scheduler then takes the job that's quality of service critical, or the other jobs that is interfering with the job that's quality of service critical, and moves them somewhere else. Okay.
What's the notion of the bandwidth allocation? Like, how do you increase or decrease the bandwidth?
Basically, you give higher priority. It depends on the memory scheduling mechanism, of course. In this case, you should read the paper for more detail. But basically, the proportion of these intervals where you're the highest priority becomes higher. And the expectation is that you get higher bandwidth that way. Again, even that's not perfect, right? Because you may be given higher priority in an interval, but you may be so unlucky that you may not be generating any requests during that interval. So all of these are probabilistic in that sense. Okay, so let's look at how we evaluate this. You have each application, we have 25 applications in total, is in turn considered the QoS critical application. And it's run with 12 sets of core runners of different memory intensities. And as a result, you get about 300 multi-program workloads. And each workload is run with 10 different slowdown bound values for this application that's considered quality of service critical. So what is the baseline? It turns out there isn't a whole lot of work, at least in the general purpose multi-core domain, where you can compare it. So one work, for example, always prioritize the quality of service critical application. If this is important, always prioritize it. Everything else, lower priority. And that's not good for overall performance, as we will see. And other applications requests are scheduled in the first ready, first come, first serve order, which you know very well by now. So let's look at one workload over here. This is a 4-core system. This is quality of service critical. These are not critical. If you always prioritize it, this is the slowdown that you get compared to when it's run alone on the same system. So even if you always prioritize it, you see that there's a slowdown. And that's about 2x here, which means that there's interference that's happening even if you always prioritize this application. So this is the best we can achieve, actually. So if the quality of service bound of this application is 1.2, too bad, don't schedule it with these applications. Maybe you should schedule it with some other applications that are not interfering as much. So that's the job of the higher level scheduler. Okay, so if the quality of service bound is very loose, in this case it's 10, which means that we want to achieve at most 10, a slowdown of at most 10 for this application, this is the performance we get. Basically, we're achieving 10, which is good, but that's a very loose quality of service bound. And you get significant performance improvement for these applications. So always prioritizing is not a good solution if you have a low quality of service bound. Right? Now let's reduce the slowdown bound. So now it's 3.33, 10 divided by 3. Now we are still achieving it. Our slowdown is less than 3, but that's an easy thing to achieve. And the performance loss is, these slowdowns have increased a little bit over here in these other applications, but they're still not bad, right, compared to always prioritizing this quality of service critical application. So the performance is actually improving in your overall system. Now let's try to make the slowdown bound even tighter. The slowdown bound is now 2. We're still almost achieving it, which is not bad. Now these guys have increased in their slowdown, but as you can see, compared to always prioritizing it, we still have lower slowdown for these applications. So the overall system performance is still better than always prioritizing this quality of service critical application. Now let's make it even more. Well, 10 over 7 and 10 over 9 is less than 1.4, and clearly we're not satisfying quality of service bound anymore, because it's not possible to do that. Even if we always prioritize it, this is what we're going to get. And it seems like we're a little bit better than that here, because it just happens that way. Because you change the interference patterns, always prioritizing may not always be the best solution, right? Because we're really changing the interference patterns if you think about that. That's why this is really not a very, very tight bound for the best we can achieve with the mechanism if you change the interference patterns. Make sense? Okay. So basically, you can meet the slowdown bound for the QoS critical application, assuming it's meetable. And you can improve the performance of non-quality of service critical applications. Of course, this is not a guarantee. So why is it not a guarantee? Whenever you have quality of service, you want to do two things. First of all, you want to meet the quality of service bound. Second of all, you want to understand or predict whether you're actually meeting the quality of service bound. Right? There are two things. You can meet the quality of service bound, but you can think that you haven't met the quality of service bound and notify the operating system saying, oh, I haven't met the quality of service bound. Or the other way around, right? You can not meet the quality of service bound, but you think that you're meeting the quality of service bound. So that's bad. In that case, you don't do anything. So this is a really bad case, actually. So you're really violating the service level agreement without doing anything about it. So this is the good case. You're meeting the quality of service bound, and you're thinking that you're actually meeting them. So almost 80% of the time, that's good. And this is not so good, but at least you're meeting the quality of service bound. Maybe you're not being efficient because you're thinking you're not meeting it, so that you're notifying the operating system. So we can meet the quality of service bound with this mechanism for about 81% of the workloads, and always prioritize, it turns out, meets the bound for about 83% of the workloads. So it's close to the always prioritizing the quality of service critical application. And you can correctly predict whether or not you're meeting the bound for 95% of the workloads, as you can see. Now, if you can eliminate these cases, that would be much nicer, of course, because this is the place where it's not doing so well. And this is happening because of the inaccuracy of the slowdown estimations. Well, I guess there are also two things, right? You may be inaccurate in slowdown estimations, and also you may not be having the right mechanism to use them. Okay, so let's look at the performance of the non-quality of service critical applications averaged across many, many workloads over here. This is a number of memory-intensive applications that you have in the system. And this is the performance you get in the non-quality of service critical applications. So you basically, and if you see over here, we're again varying the performance bound. This is always prioritized. This is performance bound that's very relaxed. And this is performance bound that's really, really tight. If the performance bound is really relaxed, this is system performance. System performance for non-quality of service applications improves significantly compared to always prioritizing the quality of service critical applications. So for example, when the slowdown bound is 3.33, system performance improves by about 10%. When it's much lower, of course, system performance doesn't improve compared to the baseline, which is always prioritizing the quality of service critical application. So that gives you the trade-off, basically. Okay. And I'm not going to talk about this minimizing maximum slowdown, but you can, for example, use this mechanism not to provide soft slowdown guarantees, but have a better memory scheduling algorithm that's more fair, for example. Have a better memory scheduling algorithm that tries to minimize the maximum slowdown of all applications, because you know, at least you predict the slowdown of the applications reasonably accurately. And the paper describes one mechanism to achieve that, and it improves fairness reasonably significantly. Okay, so what else can you do? Of course, whenever you're looking at slowdowns, you need to look at the sensitivity to model parameters. That's important. So if you're actually interested in this, you should really read the paper and look at how robust the values are to the model parameters. Okay, and you can read that, basically. Okay. Any questions?
What are your assumptions that your quality service critical application is 1 or 2? Because if you increase the number of quality service critical application, and most of the time you are predicting them in the high priority mode, it will stop. Okay, if the application is 1, okay, then it doesn't.
Yeah.
But if you increase that number of applications, so
Yeah. So your point is very good, actually, and that adds another level of complexity to the problem, basically. Having more quality of service applications and having more things to satisfy the performance requirements of complicates the problem. In this case, the evaluation was done with a single quality of service critical application. And I believe there was some more evaluation with multiple quality of service critical applications, but the problem becomes more complex, for sure. That's why this is a really exciting area, actually, because there's a lot more to do to really meet this. And this is actually, this predictable performance is really one of the major challenges of computing going forward. If you look at some people write what are the biggest challenges in computation in the next 20 or 30 years, and predictable performance is always high up on the list. Enabling emerging technologies is usually high up on the list also, like how to overcome the scaling problems. But predictable performance is always high up because regardless of whatever technology you have, we really want this predictable performance. We want more dependable systems because dependable systems build on this predictable performance. But the problem is hard. It's not easy. And that's exactly the problem that you want to research. Okay, I'm not going to go through this in detail. You can read the paper, and we've already discussed almost everything over here. Okay, let's, like everything else, this is upsides and downsides. So clearly, compared to previous work, this has some simple new insight to estimate the slowdown, as opposed to trying to do the nitty-gritty calculations for every request. It sees the forest, not the individual trees. And it's much more accurate slowdown estimations than prior techniques. That should be then. So we can do online error correction. It's a good thing to do. Okay, and it enables a number of quality of service mechanisms that can use these slowdown estimates to satisfy performance requirements. And you can actually imagine more. But of course, the downsides, there are still errors, right? And as I've discussed, there are many other different sources of errors. And sometimes the sources of errors are very difficult to quantify because you're changing the interference patterns. And it's very difficult to say, oh, I'm causing error because of this reason versus because of this reason. You really need a new idea to reduce the errors. So there's still room to improve. 8.2% in the workloads that are evaluated is better than prior work, but it's still not 0%. And there's another thing that we ignored, and we've been ignoring so far. It doesn't take into account caches and other shared resources. Right? It's assuming that someone else handles them. And we're going to see that a later work actually takes into account caches. Now, caches are a little bit easier to handle, in my opinion, because you can always divide the cache and say, this is the cache you're going to get. Now, of course, better division of the cache is better, as we're going to see later on. But if you want really performance isolation, you can partition your cache. And that makes the memory problem much bigger in the end, because caches are a limited resource in the end. But they're still important, so we're going to look into that. So another place where this doesn't take into account is the interconnect. So if you have interconnect and a lot of interference that's happening in your interconnect, other than the memory bus, which this does take into account, but if you have one chip interconnect, for example, if you have a distributed cache like we've discussed, how do you take that into account? How do you estimate the slowdown in that case? And of course, if you think bigger, in the bigger system, if you have an application that's like a web search, I have a query that I'm running on, I don't know, some company's data center. I have a quality of service bound in that query, right? And how do you satisfy that quality of service bound end to end? If you can somehow estimate the slowdowns, and this is something that people are trying to do, that end to end in that large system scale, you need to take into account not only this memory interference that's happening, but also other interferences that's happening in other parts of the system. Okay, so this may be assigned as a reading sometime. Any questions? Okay, so let's look at something a little bit different, and then we'll take a break. So far we've been talking about multi-programmed applications, meaning that you have two applications that are running and they have nothing to do with each other. Right? And one is quality of service critical, the other is not quality of service critical, for example. That may or may not be an easier problem, but not all applications are like that. You may have multi-threaded applications as well. Multi-threaded application is basically you divide the application into multiple threads, and the threads actually coordinate. We've been assuming that threads are not coordinating, threads are competing so far. Okay, basically in a multi-threaded or parallel application, threads are interdependent as opposed to threads from different applications. And interdependency means the threads will synchronize with each other, right? And there are many, many synchronization points. We're going to cover some of this in a later lecture when we talk about heterogeneous multi-core systems. I assume people have done lock-based programming here. Have you guys? Who has? Okay, that's good. Who likes it? Multi-thread programming? Okay, yeah. I don't think anybody likes it. I mean, it's fun. You have to do it, of course, if you want to parallelize your application, but you're very prone to errors in the end. But barriers, have you written pipeline-based applications? We're going to talk about that. Basically, you have pipe stages, producer, consumer, software pipelining, yes. Not the pipeline that you have in your first assignment. Condition variables, semaphores, there are many, many synchronization points, basically. And because of this, some threads may be on the critical path of the execution due to synchronization, and some threads may not. Now you can optimize the program because of this. And we'll see this problem more later on. But even within a thread, some code segments may be on the critical path of execution, and some are not. Right? So let's take a look at some of these. Basically, critical sections, they enforce mutually exclusive access to shared data. And since you've written lock-based programs, you know what a critical section is. Basically, each thread may be doing exactly the same thing, or different things, but whenever they're trying to update some shared data structure, they need to lock it. Right? And this is a critical section because only one thread can have exclusive access to it at a given time. So let's look at how this behaves. This is the non-critical section, and this is the critical section. And I've said this already. If you have contention for this critical section, meaning that if this thread 1 tries to acquire this lock, while another thread is in the critical section, this gets delayed, right? Clearly, critical sections cause serialization, and they can be on the critical path, right? Contended critical sections make thread wait, which means that you may optimize it. So actually, if your program is heavily dependent on shared data, it may be bound by critical sections, and if your critical path may actually flow through this critical section over there. If you reduce the critical section time by half, you can actually improve your performance significantly. Okay, let's look at barriers. Reducing the critical section time may be something else, right? So maybe there are some other threads that are also running in the program. You don't want them to be interfering with the accesses that are made by this critical section because this is really on your critical path. If you know that this critical section is the really important code piece, maybe you should prioritize this critical section's requests in your memory scheduler. That's the basic idea, basically, I'm going to talk about. But you can use this if you somehow figure out what is on your critical path of your program. You really would like to do things to minimize that critical path. Another option, for example, could be in existing systems, you have, at least Intel systems, have the ability to increase the voltage and frequency significantly, right? That's called turbo boost. One option could be if you figure out that this is on your critical path, you increase the frequency significantly such that you get out of this critical section quickly. And then you increase the frequency of this core, and then this core, and then this core, and then that core that's on the critical section, right? So it's really a general idea over here. The critical path, if you can somehow estimate it, you can improve the performance of a program. We're going to use that in the context of memory scheduling. So barriers are another synchronization point. Basically, you need to synchronize across different threads at different points in the program. Because, for example, you may do some computation over here, and then you need the threads that are computed by other values. That's why you need to have a barrier to synchronize, so that you can start the next parallel computation across threads. So basically, if this happens, each thread is executing this code. For some reason, this thread finishes its loop earlier than this other thread, but it needs to wait for this other thread to reach the barrier. Right? Basically, threads have to wait until all threads that are synchronizing at a barrier need to reach the barrier, or reach the barrier. And the last thread arriving at the barrier is on the critical path. So this thread is on the critical path. So if you somehow figure out that this thread is going to be on the critical path, you can prioritize this thread early on, such that this kind of imbalance doesn't happen, right? Ideally, all of the threads should reach the barrier at the same time as early as possible, such that you don't have this imbalance. But for example, if you look at this picture, if you haven't realized that this thread is going to be on the critical path, your memory scheduler may be prioritizing this thread, because you have no information about this thread's importance. Right? If we use, for example, thread cluster memory scheduling, assuming that these threads are similar in terms of their intensity, maybe the thread cluster memory scheduling is shuffling these threads, even though this thread is much more important for the overall execution time of the program. So, of course, you can have questions as to why does this happen, right? This happens because thread 1 has less work to do maybe over here. Maybe it has better locality. There may be many reasons, right? We're not going to go into that at this moment, at least. But the key point is, if you can predict that this thread is on the critical path, you can prioritize it. Okay, let's look at the pipeline program. One example of a pipeline program is this. You may have a loop iteration, and you may statically divide that into code segments called stages. So, for example, this is a loop that you have. It has 3 different computation stages, A, B, C. And you can divide into threads, and the threads can execute the stages in different cores. So stage A is executed in this core. It has some inputs coming from here, or the previous iteration of the loop. And then it produces some outputs. And those outputs are fed into stage B that's running on this core. And that produces some outputs. And those outputs are fed into stage C that's running on this core. So now you've parallelized a loop iteration. And pipelining is actually very good for parallelizing within a loop iteration, not across loop iterations. Across loop iterations, you can do whatever we just discussed over here, right? So within a loop iteration, you can actually pipeline. And of course, how do you pipeline is important, because you probably want to minimize the communication between these code portions, A and B, such that they don't communicate a lot with each other, but you have very good locality of data inside A, very good locality of data inside B, and very good locality of data inside C. ... Okay, but if you look at this code, now the thread that's executing the slowest stage is on the critical path. These threads may not be, the code may not be very balanced over here. Well, okay, so this is the example, basically. For some reason, B may have a lot more work to do. The stage may be long because it's doing a lot of other things, right? A lot more things than A and C. Ideally, you would like to balance them, but that may not always be possible. Now, if this is the case, what's happening right now is B is taking much longer. You're executing the first instance of A here, the first instance of B here, the first instance of C here, but the second instance needs to wait until B finishes because B is going to produce some result. Now, this is your critical stage, if you will. And if you know that, you can prioritize the requests that are coming from this thread B in your memory scheduler. Or you could increase the frequency of the core that's running this, right? Okay. Okay, so how do we handle this? I'm not going to go into a lot of detail here, because there's a lot of detail on how do you estimate these threads, right? Maybe we'll talk about that later on when we talk more about multi-threaded workloads. Basically, the key observation is that some threads are on the critical path, some threads are not. How do we schedule the requests of interdependent threads to maximize multi-thread application performance? And the idea is somehow figure out which threads are limiting, which threads are likely to be on the critical path, and prioritize their requests. So that sounds reasonable. What do you do with the other threads? Well, the other threads, you could employ some scheduling policy like thread cluster memory scheduling. You shuffle the priorities of non-limiter threads such that you could reduce the memory interference among them. So how do you estimate which threads are limiter threads? That's the hard part here. Well, one would be you can figure out the thread that's executing the most contended critical section. You need to somehow instrument the critical sections this way, and we're going to talk about that later on in heterogeneous multi-core, because one other way of accelerating these critical sections could be actually shipping the critical section to a large core that can execute it much faster. Right? Okay, thread executing the slowest pipeline stage, how do you figure that out? Again, you may instrument the code if you know these boundaries of the pipeline stages, which you hopefully know if you're programming in a nice fashion. And thread that's falling behind the most in reaching a barrier. How do you estimate that? That may be the hardest, actually, because you need to have a notion of progress within a thread. And if you don't actually know what's the notion of progress, this is hard to do. But if you know the notion of progress, it's not that hard to do, right? Okay, but I'll leave you to read the paper to go to the details of this. Otherwise, it'll take us a long time at the moment, and it'll derail us. But we're going to get back to some of this later. So let's take a look at how this works. This is a little bit more complicated right now. So we have 4 threads in a multi-thread program. Non-critical sections are these thin lines. We have 2 critical sections, the green ones and the orange ones, and we have a barrier at the end. And basically, this is idleness. You're waiting for synchronization or lock. And this is the critical path that I'm going to draw. So if you want to know the critical path, you cannot go forward. You have to run the program, and you have to go backward. Right? So the critical path analysis actually is not so easy online. It's easy to do it offline. So once you know this is the execution, you can easily figure out where the critical path has been, right? And in this case, I've drawn the critical path. It really goes through this green critical section, green lock, because that's really the limiter. That's really causing a lot of the waiting, as you can see over here. This thread is delayed because it's waiting for this. This thread is delayed because it's waiting for this. This thread is delayed because it's waiting for this. This thread is delayed because it's waiting for this. This thread is delayed because it's waiting for this, ... And then eventually, this thread becomes the critical path. It's the last one that's reaching the barrier. Okay, so if you somehow estimate threads that are limiters, so let's assume that you run the program for a while and you figure out that, oh, this lock is the most contended lock, so I'm going to prioritize the thread. I'm going to designate the thread that holds that lock as the limiter thread, and I'm going to prioritize it. So you figure that out here, over here with some profiling. And limiter thread is now D, and it gets prioritized. Basically, its critical sections now take shorter because we're prioritizing it. We're not prioritizing this other thread that is not critical. And if you do that, this is what happens. Basically, the threads that are that need to enter these critical sections take smaller amount of time in those critical sections, and they reach the barrier much faster, so you save some cycles. That's the idea, basically. Of course, if your profiling is much more accurate and much faster, you can save more cycles. And the key question is, how do you actually adapt to changes, right? Because when you reduce the critical path, some other thing may become the critical path, so you need to adapt to these changes also. And clearly, I haven't shown you what we have done with the barriers over here. So if someone provided you a notion of progress in this thread, maybe you could have improved the performance better over here. And the paper talks about that, but we're not going to deal with that over here. So basically, the key idea is to identify the limiter thread and prioritize it, and hopefully you'll get to the end of execution time much faster. Okay. And now your critical path is still through the green thing over here, but these parts of the green lock took much shorter compared to these parts, because you figured out that that was your critical path. Okay. And if you read the paper, this improves performance on multi-thread applications, and the performance improvements are significant. But I'm not going to go into the detail. So what are the upsides? This is the first thing that we've seen that improves the performance of multi-thread applications, that takes into account the synchronization, right? Everything else assumes that there is no synchronization. And this is important. If you want to do estimation of a real parallel application, you have to take this into account somehow. And there's a mechanism for estimating limiter threads that we have not talked about, but I've given you the high-level idea. And it opens a path for slowdown estimation for multi-thread applications, although that's not really analyzed well, and there's not a lot of work in this area, actually. How do you estimate the slowdown for multi-thread applications? It's a more difficult problem than estimating the slowdown of a single-thread application. It's a fascinating problem, actually. If you're interested in working in this, I'd love to talk about that. So you can see that the problems are becoming bigger and bigger. So there are clearly downsides with any mechanism. One is, what if there are multiple multi-thread applications running together? I should say that this is limitations, right? Because this doesn't handle that case. This is looking at a single multi-thread application where the threads are contending with each other. But if you have multiple multi-thread applications now, maybe you do this separately for these different multi-thread applications, but now you have the multi-programmed scheduling problem between those multi-thread applications. So there's another level of complexity there. And limiter thread application estimation can actually become complex. And it may not be perfectly accurate. It's not actually, I know that. But this is important, I think. There are a lot of potential applications if you can do this well. Okay, so that's the paper. And this is a really good time to stop unless you have some burning questions before we stop. Or you can.
Your idea is somehow similar to pipeline balancing.
Mm-hmm.
Your idea is somehow similar to pipeline balancing, like to make each stage equal amount of work so that they progress in due time.
That's right. So basically, you can actually improve the so there's a huge body of literature on improving multi-thread application performance, certainly. You can actually try to do that in software, for example. You could try to do load balancing across these different threads. If you have perfect load balancing, which is a really good thing to do, but which is really hard to achieve in practice, then the barrier estimation will not buy you much. So that's one potential thing. But then the contended lock estimation is very different from pipeline balancing, the load balancing, right? That has nothing to do with load balancing, actually. You really want to estimate which lock is more contended in that case. Of course, there are other software optimizations that you can do to eliminate the locks, right? But that's also very hard to do in practice. So again, this area is a very fascinating area, and there's a lot of other work, but within the context of memory scheduling. Yeah. Okay, any other questions? Are people ready for a break at the moment? I think so, yes. Okay, let's take okay, I'll give you a 9-minute break today. And then we're going to do exponential back off. Just kidding. Okay, let's continue. I think that's 9 minutes, and we've achieved the performance target. And because I had no interference at Tannenbar, I achieved my performance target also, so that's good. Because I needed to satisfy something. And you can imagine what that is. Okay, so we've covered a lot of ideas in memory scheduling. There's a lot more, as I said. Now we're going to switch gears a little bit and talk about some other ways of handling memory interference. And you remember that we talked about this a little bit also earlier. But we're going to do a better treatment of it right now. Maybe not as detailed as memory scheduling. Okay, this slide you've seen before. And these are fundamental interference control techniques. You can apply these anywhere where you see interference. You can apply these in real life also. And we're going to look at the second one, which is data mapping to banks, channels, and ranks, focusing on channels in this case. But you can imagine the idea to be extended to banks, ranks, subarrays, or any kind of structure that you can partition across different applications. Okay, and this is another slide that you've also seen before. Remember, we were talking about smart resources versus dumb resources. This is an example of a dumb resource approach. We're going to keep the resource as dumb as possible, meaning we're not going to put interference control and reduction mechanisms into it as much as possible again. We're going to change that. because as I said, the best is really combining both approaches. But let's start with this approach. This is trying to make the resource as dumb and as simple as possible. And the idea is memory channel partitioning, and the observation is that you have multiple channels in existing systems, and that provides a new degree of freedom. You can map different applications to different channels. So in current systems, what happens is applications get actually mapped to all of the channels, and as a result, they have interference with each other, as you can see. The operating system, for example, when it allocates an application's pages, it doesn't consider which channels it's allocating from, if it's not interference aware. And this causes interference between applications requests, and then we try to resolve that interference by prioritizing things appropriately in the memory controller, right? Now, wouldn't it be nice if we could do this? We basically partition the allocation of channels to applications such that the red application gets allocated only from this channel and the blue application gets allocated only from this channel. Now we've eliminated the interference that happens in main memory, which was not possible at all to do with request scheduling, right? Request scheduling is reactive in the sense that it reacts to the interference. It can still be proactive, it can predict the interference, but reactive in the sense that it tries to resolve the interference after it happens or while it's happening. Here, we can eliminate the interference completely. Of course, this is a nice idealized picture. If you have two applications and two channels, this may work. It may not work if this application actually requires a huge amount of memory, right? You don't want to restrict it to only a single channel. So you will still inadvertently cause interference, but at least you can be more intelligent about it. You can minimize that interference by trying to allocate as much as possible from this channel for this application, right? So it's clear that this is an ideal picture over here, because there are reasons for these channels. You may get more memory capacity because of the channels as well, right? And also, even if you have, usually in existing systems you have, let's say, 4 channels or so, but you may have 24 cores and 24 applications, right? Clearly, you're not going to be able to isolate 24 applications in the 4 channels that you have. Okay, so the overview is, the goal is to eliminate harmful interference between applications, and the basic idea is to map the data of badly interfering applications to different channels. So we don't want to isolate everything. We want to isolate stuff that badly interfere with each other. And there are 2 key principles in this work, at least, and you're more than welcome to develop many more key principles, and I think this is an open area still. We want to separate low and high memory intensity applications because, as you know from before, these destroy each other's performance a lot. And we try to resolve that with memory scheduling. Remember thread cluster memory scheduling, or Atlas. If something is low memory intensity, prioritize it such that it can make progress in its core. But if you actually allocate a different channel for all of the low memory intensity applications, that also solves that problem. And also, we want to separate the applications that have low row buffer locality and high row buffer locality. Again, this is very fundamental. Remember the niceness that we discussed yesterday? An application that has high row buffer locality is not nice to other applications, assuming you have a particular memory scheduling mechanism that prioritizes row buffer hits. So if you separate the not nice applications from the nice applications, then with partitioning, you can get good isolation. Okay, let's take a look at this. High memory intensity applications interfere with low memory intensity applications and shared memory channels, and we've seen this before. This is one picture over here. The red application is highly memory intensive. The blue application is not very memory intensive, and if you actually put them into the same channels, blue application gets delayed a lot. Whereas if you partition the channels, this is what you would get. In fact, this is a really nicely cooked up case that shows that both applications' performance improves, right, in this case. Not only this one, but also this one. It may happen, though, in real life. Even though it's cooked up to motivate this approach, this may actually happen in real life. And we see that it actually happens. So you can actually improve both of the applications' performance by isolating them, which was not, again, possible to do with memory request scheduling. Okay. And the other key insight is you have high row buffer locality applications. They interfere heavily with low row buffer locality applications. And we've seen this before. This is another example of this. This red application has high row buffer locality. The blue application doesn't have good row buffer locality. These are rows. So R0 is, the requests are to the same row. And this doesn't exacerbate the problem. But here, the memory scheduler reorders requests are 0 before these other requests, and as a result, these take a long time because they're all robot for conflicts. And this is with conventional page mapping. But if you actually separate these applications into different channels, again, this is what you get. You save cycles in this application here. I couldn't cook up a case where this application's performance improves over here, but you could easily cook up a case for that as well. But clearly, you're improving performance, overall system performance, by providing isolation in this case. OK, so how do you actually do this? I'm not going to go into a whole lot of detail here. Again, the paper has a lot more detail. I just want to give you the high-level ideas. You need to somehow figure out, profile the applications, somehow figure out their characteristics. Right? You could do this statically or dynamically. Dynamically is usually a good idea. And then after profiling, you classify the applications into groups: high intensity, low intensity, high robot for locality, low robot for locality. And then you partition the channels between application groups. And then assign a preferred channel to each application. So clearly, we don't have 2 channels, 2 applications. We have 4 channels and maybe 60 applications, right? So that's why you need to group the applications in terms of their characteristics. And I say a preferred channel here because you don't want to hard partition the channels. If an application demands more memory than a channel can provide, you really want to be able to allocate from that other channel. Because if you don't, you have a much bigger problem at hand. You cause page faults, right? So it's really a preference to mitigate interference. So you don't want to you don't want to cause a bigger problem for solving the memory interference problem, right? Okay, and then allocate applications pages from the preferred channel first. And if for some reason you need more pages and you cannot allocate from that channel, then you go into the next channel. Okay, so how do you do the profiling? In this work, it's done in hardware. And hardware is a good place to do that because you know the interference patterns, you know the robot for locality and intensity at a much finer grain. And everything else is done in the system software in this work. So this is more of a hardware-software cooperative because system software has control over which channels are allocated to which applications pages, right? So clearly there's some overhead in doing this in system software. You could do it in hardware also with additional complexity. Like one of the takeaways at the end of this course should be, you can do anything anywhere, software or hardware, as long as you have a good hardware base to begin with. So you can put the system software completely into hardware, right? But this is maybe a good partitioning of work over here. Okay, so this again operates interval-based. You profile the application in the current interval. At the end, you classify the applications, partition the channels, and assign preferred channel to applications. And when the application requires some page allocation, in the next interval, you enforce the channel preferences. You start allocating from the preferred channels. Make sense? Okay. So for more detail, you can look at the paper. But there are some observations over here. One is let's assume that you partition the channels between low memory intensity applications and high memory intensity applications. Now you may have a problem here because you have a lot of you have the same channel bandwidth in the same channels, but the low memory intensity applications are not using that bandwidth that much. So you have a load imbalance between the channels. If you put all of the high memory intensity applications to one channel and the low memory intensity applications to another channel, maybe actually lose performance because you're not using overall your aggregate channel bandwidth very well. So the idea is the first observation is that. So maybe this is not a good idea after all. And these applications have the most potential to keep their cores busy. We really would like to prioritize them. So instead of handling these applications with partitioning, maybe we do something else. Basically, because these applications actually interfere minimally with other applications because they have very low memory intensity, why not prioritize them? So that's the idea. Now we are actually combining multiple techniques. It turns out this is better than just partitioning or just scheduling. The idea is to always prioritize these very low memory intensity applications in the memory scheduler, not do partitioning for them, allocate data from all channels, potentially. And for other applications that are not very low memory intensity, use the memory channel partitioning mechanism that I described to mitigate the interference. Now it turns out this is better. This is better than just doing channel partitioning or memory scheduling. or application-aware memory scheduling, as we've discussed before. And I'll give you some results. Does that make sense? So in the end, I think the higher level takeaway, which I'm going to tell later again, is you really want to treat the applications with the technique that is most suitable for them. If something is low memory intensity, then you would like to really prioritize it as opposed to wasting precious channel bandwidth by partitioning them to a particular channel. Okay, the cost of this actually, if you just do memory channel partitioning, there is no modification to the memory scheduling logic. That's going to be one advantage of this. You just need profiling counters and hardware, and then everything else is software-based. If you actually integrate the memory partitioning and scheduling, you just need a single bit per request. So the memory saying that this application is low memory intensity, and prioritize that application over other applications, which is not that complex compared to other schedulers that we've seen. So the complexity is clearly much lower with this kind of approach in the memory scheduler. And I mean, take all of these results with a grain of salt. This is averaged across a bunch of workloads a long time ago, like 6 years ago or so. And as you can see, this improves performance higher than compared to other approaches. These are some memory schedulers of the time, and memory channel partitioning actually improves the performance over the best memory scheduler. And if you actually integrate memory channel partitioning with the memory scheduling, prioritizing low memory intensity applications, you get even higher performance. Okay. Okay. Any questions? No? Okay, so all performance results should be taken with a grain of salt. Maybe I can give a lecture on performance analysis in the future, because it really depends on the system you're designing, the workloads that you have, the time that things are evaluated. So this is performance results from 2010, actually. So things may be different today. Maybe this is actually a much better mechanism today. I don't know. It also depends on the assumptions you make in the system. But the key is understanding these trends over here. That's why I think the most valuable part of this course is where we discuss the trade-offs. What are the upsides and downsides, advantages and disadvantages of the mechanisms, right? Because no mechanism will be exactly the same when you apply it to some other context in the end. So basically, one of the key takeaways over here is combining multiple interference control techniques. And this work shows that combined interference control techniques can mitigate interference much better than a single technique alone can do. The key challenge, of course, is deciding what technique to apply when, and partitioning work appropriately between the software and the hardware. Let's look at this MCP, memory channel partitioning, and integrated memory channel partitioning and scheduling. Let's look at the pros and cons. The upside, now you keep the memory hardware, scheduling hardware simple. We don't keep adding more complexity to it. Not so bad. It combines multiple interference reduction techniques, the second one over here. And it can provide performance isolation across applications mapped to different channels. This is not a direction that was pursued in the past as much, but I think there's a lot of potential over here to extend something like this to provide more performance isolation together with scheduling. And the general idea of partitioning can be extended to other granularities, which I'm not going to talk about. There's other work that came after this that talks about bank partitioning, for example, partitioning banks across different applications. And I think you can even go to the smaller granularities and do subarray level partitioning if you really want to get even higher performance. Of course, like everything else, it has downsides. One is this. What if workload changes behavior? Now, if a workload changes behavior, a memory scheduler can adapt to that much more easily because it's really changing the priorities relatively quickly. But now, you profiled and you figured out an application has low memory intensity, and you decided to spread all of the pages across all the memory channels. And then the memory and the application changes behavior quickly, and it becomes very high memory intensity. It starts pounding on all of the pages that you've allocated across all of the channels. How do you fix that problem? Well, if you're doing purely memory channel partitioning, what you really want to do is get back those pages into a single channel, right? Well, that's expensive. You're moving a lot of these pages across channels. So you really need to have some other mechanism to handle this workload changes. This mechanism alone cannot handle it very well.
To lower the priority?
Yeah, exactly. So that's another mechanism, right? That's basically another mechanism. You need to change the memory scheduler still to change the the mechanism in its purity cannot handle the workload behavior changes very quickly. And of course, if you want to handle it by actually moving pages, so in some cases you may actually want to do this. You want to move pages between channels when the workload changes behavior, assuming you think that actually the workload is going to be stable for a long time, right? If you have that information, this may not be a terrible idea. But of course, this restricts your benefits, right? Because that adds overhead into getting the benefits of the mechanism. Okay. Any thoughts? So I think this argues for even more complex mechanism that takes into that is able to adapt to workload changes.
The invocation interval of like this software, because you know the page faults are not very frequent, and you can like you have to wait for very long, like even your profile. So maybe it will take a lot of time. So reacting is not so fast, in my opinion.
Yeah, reacting is not fast because you need to move the pages. That's right. Yes, it's and page faults may or may not be frequent. But reacting is difficult because you need to move the pages somehow. Yeah. And this is a very open problem, moving pages between memory controllers. How do you do that? Remember the row clone approach? It doesn't move pages between memory controllers. It moves pages within a DRAM chip. That's fast. But between memory controllers, between memory channels, there is no easy way at the moment. So this is where emerging memory technologies may potentially help if you can stack a lot of memory together and you can control it with different channels. Then you can potentially apply these ideas much better in those contexts. Okay, and that's the paper. Okay, let's move to something else, which is another completely different approach, which is core and source throttling, which we briefly discussed yesterday, right? Internet, for example, does congestion control with core or node throttling. If you're experiencing a lot of delays in your packets, you basically back off a little bit, such that you don't cause more congestion. So we're going to apply similar ideas in multi-core systems. So throttling the GPU may be a good idea, for example, sometimes if the GPU and CPU are actually sharing resources. I'm not going to talk about some of those works. They exist. If you're interested, I'd be happy to talk about them and provide references to you. I'm going to look at the general multi-core context. So let me motivate this from a different angle a little bit. So what we've been doing is we've been putting intelligence into the resources, right? Shared cache, memory controller, although we haven't put much intelligence. You assume that we can put intelligence over there, interconnect banks. If you have these smart resources approach, you will have independent interference control mechanisms in the caches, interconnect, and memory. And they may actually contradict each other. You may design a cache that provides some performance isolation between different applications and a memory controller that does something else. And they may actually contradict each other. As a result, you may get worse performance. So you really need to coordinate these mechanisms such that you get the best performance out of it. So the smart resources approach, where you make a smart memory controller, smart cache, smart interconnect, actually is more complicated than just having each of them smart, because you need to actually coordinate them as well. And this paper actually analyzes that a little bit, but I'm not going to talk about that in detail. So one of the key questions is, how do you enable fair sharing of the entire memory system, not just one resource, by controlling interference in a coordinated manner, in a simple manner? And that's where the idea of source throttling comes in. It's a general fairness substrate. And the key idea is manage the interference at the cores, at the sources, not at the shared resources. So if you think of the shared hardware resources as this cloud, you don't do management inside the cloud, you do management outside the cloud. Whatever is injecting into that cloud, you actually do management outside that boundary. And to be able to do that, you need to have information, and that information has to be monitored somehow. And how do you monitor it is always a question. So this paper monitors it by dynamically estimating unfairness in the memory system. Internet, if you think about it, monitors it by looking at how long each packet has taken. You could actually monitor it in different ways. You could actually have more information in the internet. You could figure out which paths are congested in the internet by figuring out where the packets are delayed, right, and feed back that information to the sources, right. But that adds more complexity. So in this case, we're going to estimate the unfairness in the system, feed back that information into a controller that's sitting a little bit outside, and that controller will throttle the core's memory access rates accordingly to achieve some target. Basically, whom to throttle and by how much to throttle depends on the performance target that somebody provided to you. It could be throughput, it could be fairness, it could be per thread quality of service. Again, performance could be that one. Okay, for example, if the unfairness is greater than some system software specified target, then you can throttle down the core that's causing the most unfairness and can throttle up the core that was unfairly treated, similar to stall time fair memory scheduling. But if you know the slowdown of an application, you can again do something similar. For example, if an application is not meeting its slowdown, what you can do is you can throttle it up as much as possible, and you can throttle down the other cores such that they're not causing interference with the application. So what you can do over here in throttling is limited by what information you can gather as to what's happening inside this cloud of the memory system, right? Okay, so you should really read that paper for a lot more detail over here. But let me give you a little bit more detail. So this is based on two components. Again, it's interval-based, so it's prone to all of the issues with all of the interval-based techniques. We have a runtime unfairness evaluation component that's in hardware. It dynamically estimates the unfairness or application slowdowns in the memory system and estimates which application is slowing down which other, which means that you really need performance counters to figure out those interference patterns. And you have a dynamic request throttling component, which could be hardware or software, again. It adjusts how aggressively each core makes requests to the shared resources and throttles down the request rates of cores that are causing unfairness. So you can limit, for example, how many miss buffers that you can allocate entries from. You can limit how often you can inject into the memory system. In existing systems, you can reduce the frequency or voltage. That's probably not a good idea, because if you reduce the frequency and voltage, you're actually affecting the core's computation capability as well. So you don't want to do that to solve the problem of memory interference. You don't want to penalize a core, the speed of computation inside the core if it's not causing interference. Okay, so let's look at this pictorially a little bit. Again, I'm not going to go into detail on how do you do this exactly, but you have the slowdown estimation in one interval. How do you do that? So you basically estimate the system unfairness. You find the application with the highest slowdown, slowest application. You find the application that's causing most interference for the slowest application. Let's call this interfering application, which means that you need to estimate the slowdowns. So you're back to that estimation. Again, you may not need to be perfectly accurate depending on what your goal is. So you have an unfairness estimate over here and a slowest application and the application interfering. And then you feed that information at the end of the interval to the dynamic request throttling engine. And that checks basically if the performance requirements are satisfied. If they're not satisfied, you throttle down the thing, the culprit basically, the application that's causing the problem, by limiting its injection rate and parallelism, and you throttle up the thing that needs to be elevated, the application who is not satisfying its performance requirements. So that's one example. And this is very general. You can have many different potential targets over here, and you can do many other things over here potentially, right? Okay, so basically the goal of the dynamic request throttling, let's focus on this one. You can imagine how this one works based on what we've discussed, right? You could actually have similar mechanisms to stall time fair memory scheduling. Of course, it's a little bit harder here because you need to handle the caches and the interconnect, ... So this actually adds a lot of complexity into the system, this part. Okay, so the request throttling engine, it adjusts how aggressively each core makes requests to the shared memory system. And there are two mechanisms. You remember the status handling registers, miss buffers. You can have quotas over there. You can control the number of concurrent requests accessing shared resource from each application. And the request injection frequency. You can control how often memory requests are issued into the last level cache or the shared resources from the miss status handling registers. And you really need to control both of these, actually, it turns out. And this is where things get a little bit hairy. Because what are these quotas, right? That's always a problem with fairness. Whenever you want to do a fair distribution of resources, in real life as well, you run into these real problems. Who gets what? and how much do you throttle? And that's, as we will see, this is going to be the Achilles heel of these mechanisms in general. So throttling level, you assign, in this work at least, we assign a throttling level to each core based on whether it's causing interference or not causing interference. And basically, depending on how things change over here, we throttle up or throttle down these quotas. So for example, if the throttling level is 10%, you get an MSHR quota of 12 entries, and you can inject only every 10 cycles. Now, you can immediately see the problem, right? With this approach, how do you figure out 12? How do you figure out 10? Okay, maybe you figured that out well. How do you figure out everything else? There are a lot of thresholds here, a lot of numbers. And it becomes very difficult to optimize this. So I think of this as a lot of moving parts. There are many, many moving parts. Even optimizing one of them is hard. How do you optimize, I don't know, 50 of them? That's the difficulty with these approaches in general. That's also the difficulty with internet, for example. How do you figure out whether congestion is happening? How much do you need to throttle a particular source? When do you unthrottle that particular source? These are actually things that affect performance, fairness, throughput, everything, right? And it's very, very difficult to optimize it very well. I mean, you can, with today's environment, you can say, oh, I'm going to throw a neural network into this, and it's going to figure out all of this. Maybe that's a good idea, actually, in this case, because it's very difficult to do for a human, in my opinion. Okay. But the idea has merit. The difficulty is, it's really the devil is in the details, and how do you actually optimize over here? Okay, so system software support, you can actually configure, the beauty of this is you can configure different fairness objectives. For example, you can keep maximum slowdown in check. That could be the thing that you check at the end of an interval, whether you're satisfying a target maximum slowdown in the system. You can keep the slowdown of a particular application in check to achieve a particular slowdown target. For example, if you know the slowdown, if you estimate the slowdown of an application, you can check whether it's satisfying a particular target slowdown and act accordingly in the request throttling, and ... actually. And you can have support for thread priorities as well, and it's actually a nice way of doing it. You can weight the slowdown with the weight of an application. So if a thread has higher weight, the slowdown looks much higher. So for example, a 10% slowdown, it may look like a 100% slowdown for a thread that has a weight of 10, right? That's how you can incorporate thread priorities in this. Okay. Okay, so I'll give you some takeaways. I'm not going to go into any detailed results over here. But it turns out, in the evaluation, source throttling alone provides better performance than a combination of smart memory scheduling, PAR-BS in this case, and fair caching. Fair caching meaning you actually isolate, give different portions of the cache to different applications. Because it turns out decisions made at the memory scheduler and cache contradict each other. And source throttling is a much better way of handling things more globally, right? Because it doesn't care about cache and memory controller and interconnect individually. It takes into account the slowdown in all of them. As a result, it can make better coordinated, more intelligent decisions. But it turns out neither source throttling nor the smart resources approach provides the best performance. So you really need to combine these approaches, and they're more powerful. And the key question always is, how do you combine these approaches? And that's an open question still. That's not resolved in any system that I know of today. Okay, so let's look at the ups and downs of the source throttling approach itself. It's easy to implement. The throttling portion is easy to implement. No need to change the memory scheduling algorithm. But we'll see that there are complex parts to implement, which is really optimization of these thresholds, and also getting the information that you need to actually do the throttling. That's the really hard part. Okay, and can be a general way of handling shared resource contention. You can actually handle many, many resources at the same time. And one of the benefits that we have not discussed, which is really important actually, is you can reduce the overall load or contention in the system this way. You cannot achieve this with partitioning. You cannot achieve this with scheduling, but you can achieve this with throttling. If you think about it, you have some capability of handling load in the system. And if you put too many requests, your system thrashes. Actually, there's a load latency curve, which, okay, I'm not going to put that up. But how do I draw this over here? All right, I'm going to use this. Anybody help me with that? Oh, okay. Why don't I use this? That sounds like a good idea. Do you guys know about the load latency curve? Well, that's moving up. Yes? No? That's a common thing in the internet, for example, or networks. We're going to see that in the networks later on. I need a paper. All I want to do is a load latency curve. Nothing more complicated than that, but I guess if that's what it takes, that's what it takes. I have a pen. So how do I switch things? Do you see it? Okay, perfect. So basically, all I wanted to do is draw this. This is load. This is latency. And this is 0. This is, I don't know, 100%. And usually, oh, you cannot see it? That doesn't look good. So we need to do the autofocus somewhere here. It's working. I'm not sure if it's working. Okay. I can lock it. That's not good. So somebody needs to solve this problem also. Okay, that's much better. Now you can see that's 100%, that's load, that's latency. And usually in systems, as you add more load, you get a curve like this. That's the load latency curve. And this is called, well, it's not necessarily 100%, sorry. Your load may be at 30%, depending on how you handle things. But this is called the saturation throughput, or saturation load. You basically saturate the system at this point, and your latencies shoot up. You basically overloaded your system. Remember the Tannenbar revolving door? There's a point where this latency shoots up. I don't know what that point is, but you can empirically find that out. Similarly, in any network or any system where you're injecting stuff into, you can figure this out, actually. It's very general. Ideally, you would like to operate at a point that's around here, right? You don't want to be operating at this point because you've saturated at that point, and you cannot do much. And the beauty of source throttling is you can push toward here. Once you figure out that you're at the saturation throughput, or you're close to the saturation throughput, you can stop injecting into the system, and as a result, you will operate at a much nicer point. And you can handle all of the interference much more easily that way. So you cannot do this with other approaches. The source throttling has a unique approach that provides this. Okay. Is that clear? Okay, perfect. So now you see the real benefit of this approach. Of course, you need to figure out when to do that, right? So disadvantages. One way of doing that actually is monitoring the latencies, right? We haven't talked about that, but you can monitor the latencies that average request latency, for example. You can keep monitoring it. If that's shooting up at some point, you start throttling the sources. That's a different source throttling mechanism. So disadvantages. In this particular case, you require slowdown estimations, and this is difficult to estimate, and we know that. It's more difficult to estimate if you're looking at the entire system. And thresholds can become quite difficult to optimize. So the complexity is really in how to control this. That's true for what I just described also. If you want to actually monitor the latencies and figure out when the latencies shoot up, you want to be careful about doing that. So if you don't optimize your thresholds well, what might happen is you may throttle too much. As a result, you lose a lot of throughput. Why? If you throttle too much, you're underutilizing your memory system, right? You're operating at a point over here, 0% load maybe, almost. And if you throttle too little, then you're operating at this point, which is also bad. And that's the Achilles heel of these mechanisms. How do you optimize these thresholds? And if you have a good neural network, I'd be happy to listen. Okay, and it can also be difficult to find an overall good configuration across many workloads, many applications, changing interference patterns, ... So this is actually a really good problem for machine learning approaches to take in and handle it. I'm not sure if anyone has applied it to this context, but it's really an open area. Okay, and you can read that paper, which may or may not be assigned. So this, I'm not going to talk about this, but as I said, this is a more general approach, and this has been applied, source throttling has been applied in many contexts, like networks, for example, as I said, and actually other networks as well. But I'm not going to talk about that in detail. Any questions? Let me see how we're doing on time. Okay, it's not terrible. So let's look at the last one over here, which is a different approach also, and that's scheduling applications and threads. And I've alluded to this before, right? Somebody needs to schedule these applications and threads onto the cores, and that affects the interference patterns. And the idea is to pick the threads that do not badly interfere with each other to be scheduled together on cores that are sharing the memory system. But the idea is actually more general. Depending on the system you have, you need to apply it intelligently. I'll talk about this one particular work for now. And very quickly, I'll give the key ideas. Basically, okay, maybe I'll skip this over here, but I'll talk about what kind of system that we're looking at. So this application scheduling becomes much more interesting if you have this sort of a system. Many, many cores over here. And they may be actually as powerful as these cores, but take that with a grain of salt for now. So if you have, as I've shown in the last lecture, if you have many cores, you need to interconnect them with a scalable substrate. So you may actually put your memory controllers in some parts. You may decide to distribute your shared cache across these parts. So each of these components may be maybe one or more cores, some shared cache, and a router that connects with the next component or some other components around it. Right? So essentially, you have a distributed system on the chip itself. And these have been implemented. The Tylera processor is a very good example. They have a 100-core processor that looks exactly like this, actually. It has routers in it. And Intel has its single-chip cloud computer. That was their prototype. It was called Polaris. And going forward, there will be more and more if you want to scale the number of cores. So this poses some unique problems. For example, if you get a cache hit, let me go back. If you get a cache hit, this core needs to figure out where it needs to access, assume that it needs to access the shared cache bank, and the result comes back through some other route. We're going to talk about interconnects later, but this is assuming you're doing X, Y routing. It's a simple routing mechanism where you go through the X direction first, and then the Y direction next to go to the destination. And the result comes back from the X direction first, and then the Y direction next. The reason this is good is because it avoids deadlock in routing, which is really important in an interconnection network. And if you get a cache miss, what's going to happen is you're going to do this first, and then the cache is going to ask the memory controller, get me the data, and the memory controller will wait for the data from memory over here, and then it will get the data, send it back to the cache, and the cache will send it back over here. So you can see that there's a lot of interference that may happen. If another application is requesting the same block over here, you'll interfere with the cache as well as the memory controller over here. ... Right? And if they may be requesting completely different things, but they may actually be contending in the memory controller and the caches, plus the network over here. And applications may be light and heavy, like we've discussed over here. A light application may get delayed significantly. So there are many, many issues over here, but I'm going to look at it from the perspective of scheduling applications to the cores. And that's the spatial task scheduling. You have a bunch of applications at hand with different characteristics. How do you map them to the cores? And there are many challenges over here. How do you reduce the communication distance that we've seen? How do you reduce destructive interference between the different applications? And how do you prioritize the applications to improve throughput? And you can imagine many other questions over here that are not handled. And if you're interested, you should really read this paper, because I'm not going to talk about this in a whole lot of detail over here. But I'll give you some of the basic ideas, basic concepts at a high level, again. Things that work. So clustering is usually a good idea when you do scheduling at this level. What does clustering mean? Basically, limits the reach of applications. So if you have, basically, let's say you have 4 clusters over here, you're basically saying, if I schedule this application over here, it's not going to be able to access this memory controller. It's kind of similar to memory channel partitioning, but it's a little bit beyond that, because you're really partitioning the network across applications now, right? So this application is not going to interfere with this application. So this lightweight application is not going to receive interference from this heavyweight application. So that actually provides locality within this cluster, plus it reduces the interference significantly. So that's one of the big benefits, and you'll see in the results that this actually provides one of the highest benefits in terms of reducing interference. So clustering, it turns out it's not enough. You want to balance the applications because, for example, again, very similar to memory channel partitioning, you may actually have only light applications here, but that's not a good idea, again, because you're not utilizing the resources really well if you have very low bandwidth demand applications allocated to one cluster and high bandwidth demand allocations allocated to other clusters. So you really want some balancing, some load balance across these clusters. You don't want all light applications here and all heavy applications here. Very similar to what we've seen with memory channel partitioning, except now the problem is bigger. And on top of that, you want to provide some isolation to reduce interference. Maybe some applications actually you want to isolate depending on the performance requirements. So this goes against balancing. So you really need to achieve a good balance here. And you need to read the paper as to how it's achieved. But there's a lot of room for improvement over here. And at the end, you want to improve the bandwidth utilization also. So the idea in this paper is the really high bandwidth applications should get more bandwidth from the memory controller. So they should actually be close to the memory controller. But again, you can make an argument for otherwise. This works because the low bandwidth applications are actually prioritized in the network. As a result, they can get their share. But these applications can get very high bandwidth from the memory controller. Okay, basically these are high-level approaches. This is clustering to improve locality and reduce interference, load balancing to improve bandwidth utilization, isolation to reduce interference also, and some sort of position-aware mapping of the application such that you can improve the bandwidth utilization for those applications that really need it. And that's the level of detail that I'm going to go into, except I'm going to show the clustering over here. So because it's important. So the benefit of clustering is instead of reaching and causing interference everywhere in the network and also inefficiently mapping data, we're going to limit the damage every application can cause. And in addition to limiting the damage, now you can have better locality of reference. So you don't need to go all the way to get some data from this cache over here. Okay, so this has a lot of benefit, and the paper analyzes it more. Let me give you some results very quickly. I know I'm not covering everything over here because this is a really complex problem. In fact, if you're working on machine learning, it's another place where things can be useful. In general, whenever the system gets more complicated, it's very, very difficult for humans to make the best decisions. So maybe there's some benefit for applying machine learning techniques over here also. But as you see over here, this is the baseline mapping, which is relatively random. It's actually not random, but usually you try to allocate. So you try to allocate from the closer memory controller. But the paper explores the random mapping also. If you do clustering, you can see that immediately improves performance significantly across many different workloads. And this is the workload overall intensity of the workloads. But on top of this, if you do the other things, you improve performance even more. So that's the takeaway. And you can read the paper for more analysis of the applications. And it turns out this is very efficient, very good for power as well. We haven't talked about power much, but interference is in general bad for power. If you have a lot of interference, you're wasting a lot of power also. And clustering is a good approach for reducing interference, because what clustering is doing is it's reducing not only interference, but also improving your locality. You're not reaching as far in your system. So you significantly improve or reduce network power consumption over here. And on top of that, if you do the other mechanisms, you reduce the interference and you improve the network power even more. So the network power savings over here is actually quite significant. It's more than the performance benefits that you get. So this is always good to keep in mind as well. Reducing interference is not only good for performance isolation, but it's also good for energy and efficiency. Now, that's not always true, because, for example, if you do throttling, you may actually be wasting a lot of power, right, if you lose performance. But it depends. But in this case, the techniques that are used enable you to save a lot of power. And you can read that paper for that. Okay. Let me cover this one, and then we'll stop before we get to caches, and then we'll start that after the break. Let me give you another example at the higher level of thread scheduling. By the way, any questions on the previous thoughts? Is this interesting? Have you guys thought of a distributed system on a chip before? There will be more and more of these distributed systems on a chip. That's how I like thinking of it. So it's really, you really have a distributed system, and all of the distributed system issues that we have in real distributed systems now appear on the chip. Plus, you have many, many more constraints on the chip, like power is a much bigger constraint on the chip than in a real distributed system. It is a constraint in a real distributed system, but on the chip, it's a much bigger constraint. Thermals is a much bigger constraint. Okay, so let's look at the higher level of the scheduling. I'll give you one example. It's very hard to be comprehensive about all of these scheduling issues, but I'll give you an example from scheduling in compute clusters or data centers. And data centers can be running virtual machines. And the way they do scheduling in a virtualized cluster, but virtualization is not really necessary in this case. Let's assume that you have these different hosts. You have these different virtual machines. The key question is, how do you dynamically schedule these virtual machines onto the hosts? And this is called distributed resource management. Actually, VMware does a lot of this. They have many, many products where they have these DRM policies. They try to optimize it as much as possible, ... Today, because of the single-core legacy, if you will, this scheduling is done using operating system level metrics. They look at CPU utilization, memory capacity demand, but they don't look at the interference that's happening between the cores. So I'm going to show you the benefit of taking into account that interference. So what is done today? Basically, you somehow have an estimate of the CPU requirements. How many cores do you need? Or how much CPU utilization do you need? And how much memory capacity do you need? And usually the virtual machine provides this information, maybe accurately, maybe not accurately. Actually, many times this is inaccurate. So internally, what the virtual machine, for example, the VMware virtual machine does is it tries to adapt to the requirements of the application by shrinking and ballooning the amount of memory that it provides to different virtual machines. And there's a beautiful paper by Carl Walchberger that talks about memory resource management in the VMware ESX server. It's OSDI 2012. If you really want to know how the OS or a virtual machine does memory management today, you should definitely read that paper. And you can put that online. That's 15 years ago, of course. Things have improved since then. But basically, okay, let me pull back a little bit. You have this information, and the virtual machine scheduler knows these applications. So these are actually meant to scale. This application doesn't demand a lot of CPU. It demands some memory. This application demands a lot of CPU, a lot of memory at the same time. Now, it tries to pack these applications such that you make the best use of the resources while having balanced load. So that's one way of packing the applications. Now, this may be good, but this doesn't take into account microarchitecture level interference. So what is that? Basically, virtual machines within a host compete for shared cache capacity and shared memory bandwidth. And you know this very well by now. The answer to this question is no. The operating system level metrics cannot capture microarchitecture level resource interference. So you cannot say how much interference is happening between these two virtual machines by just looking at the CPU utilization and the memory capacity demand of the virtual machines. You need to know more. And these are some real results from applications that we run. This is a streaming application. This is another application from Spec 2006. And if you run them in a virtual machine, the CPU utilization that you get for this application, for these applications, are very similar, and memory capacity requirements are also very similar. So from the perspective of the operating system, these are very equal applications. And as a result, it will map these applications. It could map these applications this way, the virtual machine manager. But if you look at the microarchitectural behavior of these applications, this application always misses in the cache almost. As a result, it demands a lot of memory bandwidth. That's why it's red. Whereas this application almost always hits in the cache, shared cache. And as a result, it demands very little memory bandwidth. And if you don't have this information, you may do the mapping this way. and put 2 of these very high bandwidth demand applications together, and 2 of these very low bandwidth demand applications together. And as a result, you have huge contention in the memory system over here and very little contention in the memory system over here. And that's the performance, overall aggregate performance that you get from the system. But if you were a little bit more intelligent, you could have done this to balance the memory bandwidth, and as a result, you could improve overall system performance significantly. And that's actually quite significant, 50% overall system performance improvement. Imagine that you're running all of these 2 applications in your data center. You're improving your data center performance by 50% in that case, by being aware of this interference that's happening at the low level. Okay, and that's that's from a conference presentation, so it's there to attract people's attention so that they don't sleep. But if they're sleeping, it's hard to attract their attention, of course. Good thing is none of you are sleeping over here. So this must be interesting at some level. Okay, so I'm not going to go into the detail over here, but you can design a distributed resource management mechanism that's aware of microarchitecture. We called it architecture because ADRM is better than MDRM, I guess. Basically, you want to be aware of the shared cache capacity and shared memory bandwidth. The key idea is to monitor and detect microarchitecture level shared resource interference. And in this particular case, you could, once you have this information, you could do many, many things, like performance isolation, for example. But in this particular case, we wanted to balance the microarchitecture level resource usage across the cluster to minimize memory interference while maximizing system performance. So that was our goal here. If you want performance isolation, you do something else. So how does this work? This is an architecture-aware resource manager, and these are the hosts. So you can think of this as running in a machine in a data center doing this resource management. And we have a profiler inside each host that profiles not only the CPU and memory capacity, but also profiles the memory bandwidth and cache misses, architectural resources. We feed this information into this global resource manager that takes into account, figures out the interference that's happening, and based on that, tries to do that swapping, for example, such that you don't oversubscribe any of the shared cache and memory bandwidth in any of the hosts. And for that, you need to be able to migrate. So these components already exist in a distributed resource management engine, actually, the profiling and the migration. We're just adding architectural awareness on top of that, such that it can take into account this low-level interference that's happening. In fact, this control is more complex than what I've shown you over here. It takes into account the interference in the storage today. So if you look at the products, for example, VMware offers, they're actually open source products also that do this. But you do need to take into account the interference in the SSDs that are happening. So if SSDs are imbalanced, you can migrate things. The key here is you should be able to migrate things based on the oversubscription of the memory bandwidth and maybe the cache capacity as well. Okay, so if you want to know more about how this works, I would suggest reading this paper and also the references that this paper provides to some of the VMware papers that talk about how things are done. Okay, before we move on to caches, let's talk about the advantages and disadvantages of this interference-aware thread scheduling. Not necessarily the high level or the low level, but thread scheduling in general. Clearly, the advantage is you can eliminate or minimize interference by scheduling symbiotic applications together. Symbiotic meaning applications that do not together oversubscribe the memory bandwidth, for example, or applications that are clustered far away from each other such that they don't interfere with each other, as opposed to just managing the interference. It's less intrusive to hardware, again, less need to modify the hardware resources. You just need to monitor them. Very similar to source throttling. You monitor and you do scheduling. You monitor, you do source throttling based on that. Okay. And like source throttling or like data mapping, you have some high overhead when you actually want to manage the resources. You need to migrate the threads or the data between cores and machines, right? That was actually true for the distributed network on chip that I described also. So if you make the wrong decisions, for example, you profiled the application and you figured out one is high memory intensity and low memory intensity, they change behavior. Now you need to migrate them somewhere. And that migration costs, costs latency, costs bandwidth, costs energy, ... So the cost is high. And these approaches usually don't work really well if all threads are similar and they interfere with each other. Assume that there's no difference between the threads. Then you cannot actually do much, right? If all threads are the same, you cannot do much. But if you actually are at the microarchitecture level, if you're doing memory scheduling, for example, that's one advantage of memory scheduling. Even if all threads are similar, it can manage the resources better. Remember the parallelism-aware batch scheduling? The two threads, when I motivated that, the two threads were exactly the same, right? They were both generating 2 requests to the memory system. And because the microarchitecture level scheduler was aware of the parallelism of the different threads, it could do something. But at this level, at the thread scheduling level, that's really hard to do. So you're really exploiting the differences between the threads at the thread scheduling level, at the core throttling level, ... Okay, so the best is really to combine all of these, and the key question is, how do you do this? That's an open problem. I guess I promised that I'll stop at the caches, so I'll wait until I get to the caches. So let me summarize what we've described so far. Basically, we've covered a lot of memory quality of service approaches and techniques. There are 2 approaches, smart versus dumb resources. Smart resources, quality of service aware memory scheduling was the example that we covered in detail. Dumb resources approaches, source throttling, channel partitioning, thread scheduling. And both approaches are actually effective in reducing interference, and there is no single best approach for all workloads. So you really need a combination of these approaches. And we've covered a lot of techniques, scheduling, throttling, partitioning, and I've combined request and thread over here, which may not be the nice thing to do, but I've done it. So it's really 4 of these. All the approaches are actually effective in reducing interference, and you can design mechanisms for that. And you can apply them at different levels, hardware and software. And there's no single best technique for all workloads. And combined approaches and techniques are the most powerful, as we've seen with integrated memory, channel partitioning, and scheduling. So I think this is really the takeaway in the end. Quality of service unaware memory leads to an uncontrollable and unpredictable system, and providing quality of service awareness improves performance, predictability, fairness, and utilization of the memory system. And we discussed many new techniques to minimize interference, provide predictable performance, and maybe ... over here, but I won't keep you longer before we get to caches. And fortunately or unfortunately, this is a very, very open area. There are there's a lot of need for many new research ideas for integrated techniques, and also techniques that are within a resource, and also techniques that close the interaction with the software. For example, the memory scheduler that we've discussed, we haven't discussed a lot about its integration with the software, except for the predictable performance part when we discussed mice. But there's a huge need for many, many new ideas over here. And whatever people come up with in this area actually will have a lot of impact, because this is a real problem, unless it's really complex. Okay, what we did not cover, and there's a lot more over here, how do you handle prefetches, for example? That turns out to complicate the problem a little bit, and you need to handle them well. Something we did not cover was DRAM and controller co-design. Actually, there are resources. How do you coordinate these resources? That's what this means, actually. Cache and DRAM co-design also. We're going to cover this next. We may cover this later. And I briefly alluded to the write-read scheduling, right? We didn't look at different request types. So different request types actually complicate the problem. Prefetch is one of them. Writes and reads are another one of them. We look at the request types in terms of criticality a little bit, but not in terms of the real types that you have. Coherence request is another example that we did not cover, right? And there are other things also, but I think this is probably a good place to stop. Not stop the lecture, but take a break. Okay, let's take a 10-minute break this time, and then we'll continue. Okay, let's get started. This time we missed our deadline. We're 1 more minute late. So the next time we're scheduled for a break, we're going to have one less minute.
This is just like nice to
Well, it depends on what performance target you're optimizing for, right? But this is what it just suggested is another approach for resource management, right? It's a credit-based approach, and it usually doesn't work, actually. You get credits for when you miss your deadline and you use up your credits next time you're scheduled. And people have actually developed economic approaches. For example, again, the name I mentioned, Karl Waltzberger, is one of the persons who did the VMware ESX Server Memory Manager. He actually developed a lot of techniques that are based on economics principles and scheduling for cores, stride scheduling, lottery scheduling, and some other market-based scheduling policies, which are pretty interesting. Some of them work, some of them do not work, but I'd recommend that you guys take a look at some of those resource management literature in the operating systems. If I was teaching an operating systems course, I would be talking about those, but this is not an operating systems course. But maybe there's... but in the end, it's always a good idea to take all of that in, because some of those techniques can be very powerful. The idea of lottery scheduling, for example, this was developed in 1994. I think it's the first OSDI. Is really to do proportional allocation of the CPU bandwidth to different applications. Each application has a weight, and you basically proportionally assign that. You probabilistically schedule the application such that overall, in the long run, the application gets CPU time that's proportional to the weight that it has. That's called lottery scheduling, and it's actually a very powerful technique to do things, to do resource management. Anyway, why did I go into this route? Because it just came to my mind at the moment. But I think I would definitely recommend you guys read it if you're interested in this topic. So where do we go next? Since we have only 18 minutes, I don't want to start a new topic. But if you guys are up for it, I'm going to talk about something else, a different way of doing interference reduction, and talk about a part of the system that we haven't talked about before, based on some of the work one of my students has carried. And this is an interesting work because it really tries to reduce interference at some other part of it. It's still related to the memory controller, but it's related to the memory controller in the sense that it's not the cores that are generating the request only, but it's also the I/O requests, because that goes through the memory controller today as well. And it's trying to solve that problem with a new technology by changing the DRAM a little bit. So that's something we have not covered so far, right? One other way of solving the problem could be changing the memory itself, maybe adding more ports. Okay, are you guys up for this? Or? Okay, let's see if we can do it in 18 minutes. Hopefully we can. But I think this is good for you to get exposed to, as opposed to starting the new cache direction. So let's look at how a system is organized today logically. You have processor, you have main memory, and you have I/O devices. And GPU is one example of an I/O device today. Actually, accelerators are I/O devices today as well. But clearly an SSD is over here, a hard disk is over here. So these do I/O access, they go through main memory. And CPU does CPU access, it goes through main memory. And these two things interfere with each other. And this interference actually can be much, much worse than the interference that two processors can cause to each other over here, because I/O device transfers are usually very large, right? So main memory connects processor and I/O devices an intermediate layer. So that's the logical organization. So let's look at the physical system implementation of it today. I'm going to put this to the side. I/O devices go through the processor. Well, there's a memory controller over here, so they connect to the memory controller. So physically, things look like this. Everything goes through the memory controller, which happens to be on the processor chip. And that's why you have this interference between the CPU and I/O access. So logically, there should not be any interference, perhaps. And as a result, you get this high contention in the memory channel when these two things contend with each other. And also, there's another downside of this. You have high pin count in the processor, because these need to connect to the processor somehow, right? So you get additional control pins and data pins. So the approach in this work is to imitate the logical system organization such that I/O devices can directly access main memory, so you can eliminate that contention. You have an I/O channel that's decoupled and isolated from the CPU channel. For that, you need to have some changes in the main memory. But that's one other general approach to eliminating interference, change the memory. So this is one slide summary. As I said, CPU and I/O accesses contend for the shared memory channel. And if you have a new DRAM architecture that has two independent data ports, you can reduce that contention. You can connect one port to the CPU and another port to the I/O devices. That way you can decouple CPU and I/O accesses. And we're going to see some applications of this. You can actually make the communication between compute units, CPU and GPU, for example, much more efficient this way. They don't contend with each other anymore. You can make in-memory communication faster, maybe not as fast as row clone because you're not doing it inside memory, but we're going to do it through the separate memory channel without interfering with the CPU. And you can improve the memory and storage communication on a page fault, for example. Instead of a page fault filling the memory while the processor is trying to access memory, you're going to fill the memory from a back channel. So the idea is very simple, actually, if you think about it, but it has big system-level benefits. And there's performance improvement as well as cost improvement because CPU pin count reduces in this case. So let's go through this in a little bit detail. So what is the problem? We have memory channel contention. So we have these I/O devices that are attached to the I/O interface that goes through the DMA engine today that is connected to the memory controller in the processor chip. And that causes contention over here because CPU accesses go through the same memory channel as the I/O accesses. Okay, these are some workloads. You can look at the paper for more detail. It doesn't always cause contention. This is basically some workloads that you offload to the GPU, matrix multiplication, convolution, ... as you can see. And this is the fraction of execution time that's spent on the communication only, going through that memory channel. Some applications are good because maybe they're long running, they don't communicate a lot. Maybe these are not as well optimized, or maybe they're short running. As a result, they do a lot of communication over here. So on this side, about 34% of the time is spent on I/O accesses. And the second problem with that system design is you have high cost for I/O interface. So this is a modern processor, circa 2014, 2015. Where do we spend the pins? A lot of it is spent on the power, supplying power to the processor, as you can see. Let's ignore that, because that's a little bit hard to fix. And that tells you that a lot of the cost of the processor is actually supplying power and managing power. But let's look at this part of the pins that we can deal with. So memory consumes a lot of the pins with 2 channels, but I/O interface also consumes a lot of the pins. And there's a bunch of other stuff that you need pins for. And integrating this I/O interface clearly leads to a high area cost because pins are area, pins are cost, pins are power. So this shared memory channel causes memory channel contention for the I/O and CPU access and high area cost for integrating the I/O interface on processor chip. So we'd like to fix that. So what is the approach? As I told you, we'd like to connect this directly to main memory as opposed to going through this DMA engine, which has been the hallmark of existing systems. So to be able to do that, you need to change the DRAM chip, and you need to use something called a dual data port. So you could actually use a dual port chip. But we don't want to really replicate the control ports because control ports add pins. So the trade-off is we're adding more pins over here, right, in the DRAM chip. But if you add a control port, that's a lot of pins. But data port may not be that many pins. So if you can afford that, this may be a better system balance in the end. So I/O interface goes there. So we have a separate interface over here, and you connect it that way. And you have some control channel where the memory controller now provides access to the I/O interface and actually configures how the data transfer is done. So the memory controller is still the master over here. It can decide which ports are used and who uses which ports. So we're not going to change that portion that much. And you have some DMA control over here such that you can communicate to the memory controller that, oh, I want to transfer something. So we don't eliminate all of the pins over here because you need to communicate still, since this is the master. And otherwise, there is no communication between the memory controller and the DMA controller. But you need that interface a little bit. OK. So now, hopefully, you can decouple CPU access and I/O access. And these are beautiful slides made by Dongkyuk. I had nothing to do with them, other than making them better. OK. So what is dual data port DRAM? Basically, you have this memory channel today, which consists of a control channel and data channel. And this is DRAM. It should be written DRAM over there. You have a control port and a data port if you look internally. And control ports, you can send commands. You can activate a bank. You can read from the bank, which supplies the data through the data port. And peripheral logic controls the banks and transfers data. You know this very well, but we haven't looked at this in as much detail in the past. Now, if you have a single data port, as you know, you can start activation of both banks in consecutive cycles, but you cannot transfer data concurrently, right? Remember, we discussed high bandwidth memories. You could actually do that, but that leads to higher cost. But we want to do that higher cost. There's a reason for higher cost right now. Basically, you need to do these separately. You can pipeline the access to different banks, but the data port cannot be used at the same time. And we have many banks and a single data port. And the requests are served serially due to the single data port, which otherwise you could have parallelized. So let's look at this pictorially. This is what you need to do. Your data port becomes a bottleneck. But if you had 2 data ports, you could do this. With a single control port, you could send consecutive commands in a pipeline manner, but there's no reason to pipeline the data in the data port because data is usually a lot, actually. So you could actually parallelize the data transfer. As a result, you could save cycles. And there's another reason for this. In existing systems, data port tends to be the bottleneck. Usually, the control port tends to be very underutilized. You don't send as many commands because of this disparity, right? With one command, you get a lot of data. Okay, so the idea of dual data port DRAM is to add another data port on this side and switch between the data ports. So a bank can supply data to different data ports, and somebody controls which data port the bank is going to supply data to. It's very simple. And we have a single control port. We're not going to increase the address pins, for example, which are actually larger than the data pins. Okay, so you need to add a port select signal to decide which port you're going to send the data, upper or lower. And it turns out, based on the evaluations, the overhead of this is 20 additional pins and 1.6% area in the DRAM chip. And you can read the paper for more detail. But now you get twice the data port bandwidth. And you have independent data ports. Okay, let's see how we can use this. Basically, memory controller can decide which, it can control the channel with the port select signal. So if you want to have CPU access the DRAM, you select the CPU port. If you want to have I/O access, you select the I/O port. And if you want to do something different, like directly transfer data through the DRAM between 2 components, you do port bypass. In this case, you're not going to transfer the data from DRAM, but you're going to transfer the data from an I/O device through the DRAM chip into the memory controller without adding more ports to anywhere. Okay, let's look at the CPU access mode. Basically, if you want to access from the CPU, you select the CPU channel, and the bank provides the data through the upper data port, which is kind of obvious in this case. If you want the data to be accessed to the I/O devices, you select the I/O channel. This is kind of obvious again. And the bank provides the data to the I/O channel. If you want to do port bypass, which is actually really interesting, I think, which doesn't exist in today's systems, basically, you bypass, you don't get the data from the banks, but you connect these 2 ports, and the data just flows through the DRAM chip into the memory controller. Now, you can always ask, why don't you have a direct connection between here and here as opposed to here? Well, if you already have this, you can do this, maybe with additional latency, but you don't add any more ports. If you actually add another port over here, you need additional cost. Okay, let's look at some applications of this. If you have this new system organization right now, what can you do? You can accelerate CPU-GPU communication. You can accelerate bulk page copy and initialization. And you can do better communication between memory and storage on page faults or file read and write, for example. We're going to look at these very quickly. Now we have 2 systems over here, CPU and GPU. And they both have this direct decoupled DMA interface in each and a dual data port DRAM. And that's existing systems today, actually. GPU has its own DRAM, CPU has its own DRAM. We're just changing the interface and the physical structure a little bit over here, such that this is dual data port, and you have the control mechanisms. So let's say CPU wants to send data to the GPU. It basically selects this port, sends the data, and there's a signal saying, I want to send data from the CPU to the GPU. And the GPU acknowledges it and writes the data into its memory. So there's a protocol that you need to do, but it is possible to do through this interface now, without interfering with the memory controller. So now the GPU can be accessing memory, CPU can be accessing memory. There is no interference that's caused, except at the bank level. Assuming the GPU is accessing a bank that this is trying to write to, then you have interference at that level, of course, and that needs to be managed, and the memory controller manages it. But hopefully you do this transfer in a manner that's bank aware. Okay, so in-memory communication, we've seen methods for this, like row clone inside the DRAM chip. It's not going to be as good. But for example, if you want to copy a source page to a destination page inside a DRAM chip, what you can do is you can read the source page into the I/O interface over here, and then you can write that into the destination page through this additional data port without interfering with here. So you may not actually reduce the latency of it, but you reduce the interference caused by that page copy. Okay, and this is the last one. If you want to select, get some data from a storage unit, basically you have another signal saying, I want to access storage, and you get the acknowledgement. Once you get the acknowledgement, the memory controller sets up this path such that the storage unit can write into this port. And the paper describes how these protocols, of course, work. You need to have protocols to ensure that they work correctly. So let's look at the evaluation very quickly. And you can read the paper for more detail. You need to evaluate with different workloads clearly. And this is, if you have communication-intensive workloads between CPU and GPU, these are some of the performance benefits you get. So it's significant, basically. And yeah, as you have more core counts, and this is the in-memory communication. So basically, if you're doing a lot of copies, by reducing the interference, you're improving performance. And this is performance on with different channels. So increasing the channel count clearly reduces the interference, but you still get performance even on a system that has an abundant number of channels. And you actually get higher performance improvement with many ranks because there's a lot of rank switching penalty that happens if you have more ranks. But you can read the paper for those details. I just wanted to give you the key idea. Another thing that's important here is if you have, so this is, I think this points out to the importance of looking at the overall system as opposed to a single component. So if you're optimizing the single component, maybe you want to actually minimize the pin count. For example, the DRAM chip, right? We've said before, the reason we don't want to add a wider data port is because we want to minimize the pin count over there. But there is an overall cost of the system, which is the pin count of the overall system. Well, and that's reflected over here. Basically, if you have a decoupled DMA engine, this is the pin count that you get. You actually reduce the pin count compared to a single channel system, and you reduce the pin count a lot compared to a dual channel system that has 2 memory channels. And as you can see over here, while reducing the pin count, you're actually improving the performance, and you're getting close to the performance of a dual channel system while having much, much less pin count over here. So that's the overall system optimization. And if you're interested, you can read this paper, but I just want to talk about this because it's really relevant to the interference, and we really don't have time to go into the caches at the moment. And looks like we've covered it in 16 minutes. Any questions, any thoughts? No? Is this interesting? Yeah, somewhat. Yes, there's one question.
This is also being used excessively in embedded systems wireless networks between the radio and the microcontroller.
What is being used? A dual data port DRAM or?
It's not DRAM, it's flash, but dual port.
Dual port. Yes, I think similar ideas exist actually, and they're used in very specialized contexts because it makes sense in those contexts. But that's.
While the transceiver can write into stream, they power off the microcontroller, so it's more power efficient.
I see, and then you have a separate port to communicate. Yeah, that makes sense. But unfortunately, in existing systems, because of the really big push for reducing the cost of the DRAM chip, it's not used. But there's a really good use case in commodity systems as well. But that's a very good point. In fact, these chips already exist, except they're not used in commodity systems. The dual data port DRAM idea is not new over here. It's really the use of it in the system context and the optimizations to minimize its cost. Okay, this is a good time to stop. Have a good weekend. Hopefully you all start your labs also, if you haven't done so. I'll see you next week.